All right, we are back. So we are going to discuss, we are going to continue our discussion on some of the important ideas in learning physics. So what is physics? Well, it's very difficult to define what is physics, but I would let you know what is not physics. Some people may want to find the ultimate meaning about life and something transcendental, or just they want to learn something about the meaning of why they exist. These are not physics. These are the philosophical questions. If you want to address those ultimate questions about your existence and about the idea why the understanding of why the universe exists, then you should go to religion or philosophy. That is not the realm of physics. Physics is only dealt with the description of phenomena, of physical phenomena, using the precise language of mathematics. So it's not about finding the meaning of something. Or finding why the universe is like this, or why the universe exists. It's not like it's not the ultimate aim of physics. Now, I think many of the your study will involve something like prediction. You'll be seeing a lot of prediction in your daily life. For example, when you see a financial advice on the newspaper, or when you see astrology advice on the newspaper, there would be a lot of this kind of description. For example, it involves words like positive influence, real concern, pressure likely to dissipate. You are likely to displease. You are fortunate. You are good. You are bad. So this description, this prediction are very vague. That means it is very difficult to verify what is good and what is bad, what is how displeased you are, and what is your real concern, and what is positive or negative influence. They are very vague. So if you say that the prediction, this prediction are not correct, then the astrologist will probably argue with you. I'm not saying this thing. I'm saying another thing. I'm not saying the thing at your level. I'm saying those things and another different level. So this is very difficult for us to disprove those claims. Okay, so that is an important difference between science and non-science, or the pseudoscience. The pseudoscience claim is difficult to disprove, or it's difficult to prove or disprove. But for physics is precise. That means you can prove or disprove it very easily. For example, if you ask me what is the position of the planet Mars in the sky tonight, I will give you the coordinates. I will give you these coordinates. So tonight, if you want to find Mars, you point your telescope to that direction, and you should be able to find Mars. Okay, that is very precise. If you do not find Mars at that position, then my prediction is wrong. There's no excuse for that. Okay, and for example, if you are playing golf ball, and the physics equation predict that the golf ball land as 65.4 meters beyond the point of a hitting ball, then it has to be that value. If the physics equation predicts that, and if the physics equation taking into account the initial condition correctly, all the factors correctly, that is the prediction, the precise prediction. That prediction is precise. That means it's not 65.5 or 65.3. It is precisely 65.4. So if it's not that value, this value, then your prediction is disproved. That is simple. Okay, there's no excuse for that. Now, there was a very famous philosopher of science. His name was Karl Popper. He was one of the most famous philosopher in the 20th century. When we say something about science, what he thinks science is that he would like to say to qualify as a science, if a subject has to be qualified as science, or a theory has to be qualified as science, that theory must be falsifiable. It can be disproved. That means it can be disproved. Falsifiable meant that it can be proved to be wrong. So you may be surprised why it's not verifiable. We usually, when we think about science, we usually think of science, the statement of science, as verifiable. You can verify it by using experiment or observation. Why Popper would say that to qualify as science, it should be falsifiable? Now, the first thing about there's a logical asymmetry between verification and falsification. For example, if I make a statement, all the cats in the world has a tail. All the cats in the world has a tail. That is a scientific statement. You can verify it, right? But can you verify it for all the cats that have ever existed on Earth? Can you verify that statement for all the cats that is going to exist in the future? You cannot do it. You can verify that statement for 100 cats, or even 1,000 cats, or even 1,000,000 cats. But you cannot verify that statement for all the cats that have ever existed, or will exist. Okay, so it's not easy to do a verification for all the sample. But falsification is easy. If you are able to find one cat, only one count example, if you are able to find one cat without a tail, that you already falsified the statement. Okay, so that means when you state a theory, when you state a scientific statement, you should state very clearly under what condition that the statement is falsified. Okay, and so it can give you people a precise criteria of how you can falsify it. Okay, so that is the important foundation of science. Now, Karl Popper actually emphasized that the opposite side of science is not emphasizing science is verifiable, but it's emphasizing science is falsifiable. Because it's emphasized science is open, it means that it is open to challenge. Anybody can challenge some scientific idea, but you have to provide a compelling experiment or compelling observation that falsify that science principle. And scientists are not afraid of making mistakes. In fact, scientists make a lot of mistakes during the research. Okay, in the course of this research, they actually disprove a lot of wrong theory. If you say when you see the Einstein saying E equal to mc squared, maybe before Einstein say the correct equation, he have disproved a lot of false claim. He falsified that, and after all those falsifications, he find the correct theory. Okay, so mistake actually help science to advance and make a better prediction of the world. When we throw away all those wrong theory, we come up with a theory that's better describe the world. And in another time, and in another regime, that theory may not be applicable. And in those cases, we find another newer theory. So that's how science is advancing itself. So, and also physics is some people say that physics is the mother of science because it can be falsified or verified to a high accuracy. Okay, because it's give a very precise prediction that allow us to falsify it to a high accuracy. And so physics become the paradigm of science since Newton. Okay, so that is the idea. Now, precise statement, as we have emphasized in falsification, relies on mathematics and clear deduction. Okay, it cannot rely on other language. Okay, if you give me a number, then I can check whether the number is correct by doing experiment. That is the only way for us to verify things. There are no other ways for us to verify things. So that means physics, or specifically classical physics, is closely related to mathematics. And actually, many ideas of mathematics are derived from learning mechanics. When Newton discovered the law of mechanics some 300 years ago, he actually found difficulty in describing nature. So he actually invented calculus or tools like differential equation to describe nature. So although mathematics in itself is a subject on itself, some of the mathematical ideas, some of the mathematical methods actually come from the development of physics. Okay, when physicists encounter a difficulty in describing nature, they discover some new tools in mathematics. So that allows mathematics to advance together with the physics. Okay, and because of these tools, it makes the classical physics as deterministic. That means when we are giving certain condition, initial condition, we are going to use the equation to give exact prediction of the future. Like for example, if you are given a ball, and at time 0, the ball is in this position, at this position, and is projected with a certain velocity, then by using the Newtonian equation of motion, you can predict the position of the ball, the velocity of the ball at another time, very precisely. That is deterministic, the physics principle. Now, classical physics is deterministic, but the modern physics, the quantum physics, is not deterministic. In quantum mechanics, scientists actually give you the prediction using some probability. If you project an electron instead of a ball, then scientists will, the physicists will tell you there's a certain probability of finding an electron in this position and certain probability of finding the electron in that position. So those predictions are given in terms of probability. So that is the difference between classical physics and modern quantum physics. Okay. Now, how physics works is essentially like this. When the physicists, when they saw some phenomena in nature, for example, when Newton saw the motion of the moon around the Earth, when Newton saw the apples falling down from the tree, he realized that there's the force that attract the moon towards the Earth and also the apple attract towards the Earth. And that is a force of gravity. But that is not enough. In order to turn it into physics, Newton has to go through intellectual leap, and he has to use a precise mathematical language to write down the laws that describe the nature. And that's the law of gravitation and the law of motion that Newton discovered, right? That involves intellectual leap. That's not simply a gathering of phenomena. That requires you to have a jump in your intellectual level to be able to use mathematical language to generalize all this phenomena. Okay, so that requires you to have a high skills in mathematics. And using this laws in a mathematical form, Newton or other physicists are able to derive some predictions of nature. That may involve some assumption, they may involve some mathematical derivation, but eventually they will be able to make some prediction. What are the predictions? For example, for Newtonian mechanics, if you use the Newton's law of gravitation and Newton's law of motion, you will be able to predict the motion of the moon and the motion of the planets. You should be able to predict the position of the planet at another time. That is your prediction. And after you make the prediction, you can verify that those predictions with observation, or you can verify with experiment. That is a process of experimentation and observation. And that verify the things you find. But if you find some discrepancy between the prediction and your experimental result, so what are you going to do? The first thing you want to do is to check whether you have done something wrong in your experiment, or you may need to re-examine the assumption that you have made in doing the derivation. Sometimes you may have made the wrong assumption leading to the wrong result. That is not related to the physical law. The physical law is correct, but you just have to have made the wrong assumption. So you have to examine whether your assumption is correct. And if your assumption is correct and you got the wrong result, and if that is the case, then you have to examine the physical law itself. that may be a fundamental change in the law of nature. You have to go back to this position to reinvent a new law of nature. Okay, so that is how physics is going to work. So let me quote one of the classic example in the development of physics. Now, in the 17th century, I think Newton, when he saw the motion of the moon and the falling of the apple, he has an intellectual leap because of his talent, and he discovered the law of gravitation and the law of motion. And using these laws, physicists are able to predict the position of the planets to very high accuracy. But I think in the 18th or 19th century, people find that the position of a planet called Uranus, 天王星, deviate from the prediction of Newtonian mechanics by 100 seconds of arc. So Newtonian mechanics predict the position of planets to be here. But in actual observation show that it's a small discrepancy from that position. The discrepancy is small, but it's there. Okay, so what causes that discrepancy? So different physicists have different postulates. Some physicists say that the law of gravitation may be wrong at large distance, because at that time, at the 19th century, Uranus is actually the farthest planet that is known to us. So some scientists, some physicists say that maybe when it goes to a large distance, such a large distance, the law of gravitation is failing to hold. So that might be a correction, a small correction to the Newton's law of motion or the Newton's law of gravitation. But some scientists think that otherwise. They thought that some factor may be missing in our derivation, so you have to correct it. And they actually assume that Newtonian physics is still correct, but there's an unknown planet. That unknown planet exerts a force, a gravitational force on Uranus, and that caused Uranus to deviate from this orbit. So the deviation is not caused by the mistake of Newtonian mechanics. It is caused by the gravitational force of an unknown planet that is beyond the orbit of Uranus. So the physicists work on a reverse problem. By taking this discrepancy from Newton's law, they use Newtonian physics to predict the position and the mass of that unknown planet. And they told the astronomer to look at that position to find that unknown planet. And eventually, in the 19th century, Laminia and Adam, according to the prediction of those physicists, they were able to discover the planet Neptune. So that is a beautiful story of scientific discovery. It did not falsify Newtonian physics, but it just used Newtonian physics. It's verified Newtonian physics by using Newtonian physics to predict the existence of unknown planets, to predict something that is unknown to us. So that is a beautiful story that marked the success of Newtonian physics. Okay. Now, but that does not always work. And also at the end of 19th century, some physicists found that the orbit of the planet Mercury is precessing. Okay. Now you know that the Mercury orbit is not completely round. It's not a circle, but it's an ellipse. And an ellipse has a long axis, a longer side and a shorter side. The longer side, if you look at the longer side of the ellipse carefully, you will find that that longer side, called the major axis, it precesses slowly at a rate of 574 seconds of arc per century. In 100 years, it precesses 574 seconds of arc. And that is a fraction of a degree. So that the precision is very small, but it's there. Now people use other methods to calculate they use Newtonian mechanics to calculate the attraction force between Mercury and all other major planets, including the Earth, Jupiter or planet Venus. Okay. After they include such correction to the orbit of the planet Mercury, most of this precession can be explained. But there was still a 43 second of arc of precession that cannot be explained by Newtonian physics. So eventually, who comes to the rescue? Einstein comes to the rescue. When Einstein discovered the law of general relativity in the early century, people used the general theory of relativity to recalculate the orbit of Mercury, and they find a correction term to the Newtonian orbit. And that new correction term exactly gives you the 43 second of arc discrepancy between Newtonian prediction and the general relativity prediction. And that offers a important verification to the theory of relativity that actually verified relativity. Okay, so that is again a beautiful story, because when people find that some discrepancy is there, it may be the place, it may be the correct opportunity for them to discover a new theory, a completely new theory that's go beyond Newton's prediction. And that is how science advances. Okay. So these are the real challenge to Newtonian theory. Of course, we have another challenge, other challenge to Newtonian theory besides relativity. We also, in a small world, in the microscopic world, we also have the quantum mechanics is another correction to Newtonian physics in a small world, okay, in a microscopic world. Now, in the 18th and 19th century, people find that very few mechanics problems can be solved exactly. Why? If you start with two problems, the Earth and the Moon, then it has the exact solution. You can solve it with your pencil and paper. You can write down the equation and solve the equation exactly. But if you have a more body involved, for example, you have the Moon and the Earth, but simultaneously they are affected by the Sun or other planets, the problem becomes very complicated, and you cannot have a closed form of solution using your pen and paper calculation. That is not possible. And so that is a difficulty in main difficulty in the advancement of mechanics. So later, the scientists, the physicists in the 18th and 19th century, they discovered a very sophisticated approximation method to handle this kind of problem. Okay, for example, for the Moon and the Earth system, they first solved the two-body problem that involved only the Earth and the Moon, and the effect of those other planets and the Sun, they treat as a small perturbation. Those perturbations perturb the orbit. It causes small changes in the orbit on the top of the solution, of the exact solution. And these are called the approximation method. These are the analytical method that helps the physicists to handle a complicated problem about the interaction of the planets. Okay. So even Newton say that the Moon orbit is a cause of my headaches. Because the Moon's orbit is not very simple. It involves tidal force, the deform of the Earth and the deformation of the Moon. That is not easy to solve. So if you want a very precise prediction, that is not easy. And so the physicists called Lagrange or Euler in the 18th and 19th century, they discover a lot of approximation skill to solve this problem. But now we don't rely too much on this approximation skill because we have the computer. The computer allows us to solve a very complicated problem. For example, when you eject a satellite or a spacecraft to visit different planets in the solar system, the orbit of that spacecraft may be very complicated because it's apart from the gravity of the Sun, it is also affected by the gravity of the other planets. But using a sophisticated computer, we can compute the orbit of that spacecraft very precisely. Although we cannot solve the whole problem using a pen on paper, but you can use a computer using small step calculation to calculate that orbit to a very high precision. That is mathematically not beautiful, but it's very practical, and that can be done in a very high accuracy. Okay. So in this course, you will be also involved in doing a simple problem numerically using a computer by using Excel spreadsheet. Okay, so that lets you appreciate the application of computer, application of numerical calculation, modeling in physics in the modern world. Now, doing computer modeling involves something like this. We first simplify the situation, and then we write down the important physics equation that is required to describe the phenomena, and we use a computer to calculate what will happen. Okay, and that is commonly done in, for example, weather forecast. If you are doing fluid dynamics, if you are predicting going to predict expansion of a star or evolution of a star, or you predict some complex system that involve interaction of many individuals, then you have to use a computer. So computer actually is very important for the development of physics nowadays. It's playing a more and more roles in the development of physics, and it will be dominating the development of physics in the future. Nowadays, people are even using AI, artificial intelligence, to predict the forms of the new laws of physics. Okay, so they start doing it now. Now, in what follows, I will discuss with you. I will name a few examples about physics. Originally, people thought that these questions are not science at all. But later, when we have the skills, when we have the mathematical skills and we have the experimental skills, we are able to verify them. And so that becomes a part of science. Now, the first question is about when did the universe begin? If you ask this question 100 years ago, people will say you are asking about philosophy. We don't have any we cannot have any methods to understand our universe, and we don't know how to predict it, and we don't know when it begins. Whether you have a beginning or not, we don't know, because there's a problem about philosophy. There's no real science question. But now, with the advance of technology and advance of physical theory, we are able to say that the latest observation found that the age of the universe is 30.75 giga-year. 1 giga-year is 10 to the power 9 years. Okay, so 13.75 is actually 1.38 times 10 to the power 8, 10 to the power 10 years. This is the age of the universe we know so far. And that is because we have the observation to support that. And we know that the universe, most cosmological now thought that thinks that the universe is accelerating. If you go back to about 20 or 30 years ago, most cosmological, actually, they speculate that the universe expansion rate is decelerating because the gravity is now pulling the matter together. So although the universe is expanding, but it's a decelerated expansion. But in this 2 decades, scientists are finding a lot of evidence about the universe. They observe very distant supernova. They observe the background of cosmic ray, the background of microwave background, cosmic microwave background, and they find that the universe is expanding in an accelerated manner. That means that as the universe is expanding faster and faster. Okay, and that contradicts the traditional idea of that the universe is acceleration is decelerating. Okay, and physicists also discovered that most of the stuff in the universe cannot be seen. They discovered that the universe actually is made of just a little bit of normal matter that we can see. They are the stars, and the intergalactic gas, but they compose only about 4% of the total stuff in the universe. So what about the other 96%? The other 96% of the stuff is made of the so-called dark matter, dark energy and dark matter. The dark matter extract gravitational force on the normal vector and also on other dark matter, but they cannot be seen. They are not normal matters. And here we have a dark energy. The dark energy is a kind of energy associated with the vacuum, and that causes the universe to expand in an accelerated manner. So the dark energy is responsible for repulsive force, a repulsive force that pushes the expansion of the universe to a larger size in an accelerated manner. Okay. So how do we know this? We know this not by using some fancy theory, but we know this by using advanced technology and instrumentation. We are now able to observe a very distant supernova. Now, this is a galaxy very far away, about 7 gigalight years. And we observe that there's a supernova exploding. And from the light of this supernova, we are able to measure the distance to this galaxy very precisely. And that gives us a knowledge about the expansion of the universe. Okay. We also send some satellite to observe the cosmic microwave background, to observe the background of microwave radiation left over from the Big Bang of the universe. So these are the echoes of the Big Bang, and from examining the variation in the intensity of this of this CMB across different parts of the sky, the physicists are able to tell what kind of matter are existing in our universe. And they come up with the idea that we have a dark matter, component of dark matter, and the component of dark energy. Okay. So I would emphasize that what we can know something or not is not a matter it's the matter of science and technology, but not of philosophy. Okay. So with the advancement of technology and instrumentation, we can now know the things that we couldn't have imagined before. That is the advancement of science. Now, in some 120 years ago, a guy known as J.J. Thomson, he discovered electron, right? You learn it in your high school textbook. And in just 120 years, nowadays, people are using electron to make a microscope, to see the atom, to see a structure down to the level of an atom. Okay, that's called electron microscope. And people are able to use the electron to confine, to use the atom to confine the electron waves. People are able to see now the distribution of electron waves inside this quantum coral. This is a so-called quantum coral. This is an arrangement of atoms, and there's electron waves like vibrating like water waves inside. Okay, so now we are making use of electrons to boost up our technology. We are using the property of electrons to make a very fast computer, and people are now developing quantum computers that makes use of the special property of quantum physics. Okay, so it's just happened in 120 years. And I think you have heard about the Large Hadron Collider. The Large Hadron Collider is in Geneva. It is discovering doing some exciting experiment about the collision of particles. And in those experiments, people discover new particles. Like, for example, the Higgs boson. The Higgs boson was discovered several years ago. It is the last particle, undiscovered particle predicted by the so-called standard model in the particle physics. So what will happen 100 years from now? Will people be able to use the particle or the discovery that we have now to improve our living or revolutionize our living? We don't know. But surely that is how physics advances. When we discover some new ideas, some new things, after several decades, after hundreds of years, we'll be able to apply this to our daily life and completely revolutionize our world. Okay, and we are driven by curiosity to study physics. We are not driven by some incentive to study physics. We are simply curious to know more, but that curiosity will change eventually, lead to a change in the world. Okay. Now, you may have heard about some fundamental particles, like for example, you know the electron is there, but there are two kinds of particle very similar to an electron. They are known as muon and tauon, and they all carry one negative electron charge, and they are in a family called a lepton, 輕子. And each of this particle, the muon and tauon, they are more massive than the electron, and they will decay. And each of this lepton actually is associated with a neutrino. A neutrino is a ghost-like particle. It can penetrate the matter very easily. When I'm talking here, there are billions and billions and billions of neutrinos passing through my body, and I cannot even notice it. Neutrino has very weak interaction with ordinary matter. That's why it is very difficult to detect them. And people long ago, they knew that they are neutrino emitted from the center of the sun because of the nuclear reaction happening in the center of the sun. So the sun is emitting those neutrinos. But experimentally, we are able to detect 1/3 of the neutrino predicted by theory. So there may be something wrong in our theory. Okay, that was what people are saying 20 or 30 years from now ago. Okay, and we also know that the proton and the neutron that exists in the atomic nucleus, they are made of quarks. The quarks carry fractional charge. For example, up quarks carry 2/3 of a positive charge, and then down quarks carry a negative 1/3 of the electronic charge. So if you have one down quarks and two up quarks, you have a total charge of +1, and that is a proton. If you have one up quarks and two down quarks, then the particle will be neutral, and that is a neutron. So a neutron and a proton is made of quarks. They are the more fundamental particle. So that is essentially the particle model that we are having now. We know that the electrons have the custom, and also we know that the proton and neutron are made of a more fundamental particle called quarks. Now this is a collaboration, international collaboration in a Daya Bay experiment on finding the neutrino. The nuclear reactor in a Daya Bay in Guangdong is giving out some neutrino. And this group, including Professor Zhu from our department, he is the chairman now. He has been working on this Daya Bay experiment to capture those neutrinos coming from the nuclear reactor. And by capturing those neutrinos, they're able to study this coupling angle theta. And with that knowledge, they can predict that the neutrino, this three kind of neutrino, can change from one form to another. They are oscillating between these three phases. So that's why at any time, we are only able to detect 1/3 of them. And in fact, they are changing from one form to another. So after knowing this, now people are able to detect the other two, and the neutrino puzzle has been solved. There's a complete agreement between the prediction of our solar structure model with the number of neutrinos emitted and also the number of neutrinos detected. Okay. So this is a Daya Bay experiment. This is a detector. Okay, a giant container. You pour in a lot of pure water to capture those neutrinos. The neutrinos are very difficult to capture. So these are some of the members of the team, and we have a lot of graduate students involved in this project as well, and also our colleagues. We also have a very exciting application of physics in our real lives. Let's say about 1 or 2 examples. For example, this is Xiao Xiaodong. Xiao Xiaodong is also from our department. He is working on this material, very complicated compound. And using this material, he is able to make a very thin film of solar cell. The problem of solar cell, nowadays with solar cell, we all talk about renewable energy. But renewable energy is not easy because we have to make a solar cell with very high efficiency. Okay, that is not an easy thing. The old solar cell only have an efficiency at highest, only has efficiency about 10% or so. But the new solar cell that we develop with this new kind of technology, with this new material, is very thin, and so it can cover a large area for effective capture of solar light, and also it is stable against chemical changes. It can stay for a long time, and so that allows the efficiency of solar energy to be increased greatly, and that produce extensive application prospect. Okay, so that enable low cost and high efficiency making of the solar panels. So that is one important application. Another thing is that I want to mention is the MRI. Have you ever take a MRI imaging? When people have something wrong, some disease in the brain, or if they have some problem with their organs, then they may like to take an MRI image of the body. The MRI image actually involves a lot of physics. It is about the resonance of a new atomic nucleus. Essentially, that is a nucleus of a hydrogen atom. That is a proton. A proton is actually, apart from its charge, it actually has a small magnetic moment. It's actually behaves like a tiny magnet in the atomic nucleus. So if you use a radio wave to excite it, the magnetic moment, the tiny magnet, will resonate with your external radio waves. And it will absorb your radio waves and excite it to a higher state. And then it will emit those radio waves outwards. And this is called the magnetic resonance. And by gathering those signals that the proton emit the radio waves, by gathering those signals, you are able to create image of an internal structure of a human body. And that can be done in very high precision. But that has to be done if the proton is under a strong magnetic field. When the proton is under a strong magnetic field and there's an external radio wave that will excite the proton into resonance. And those resonance will cause the proton to emit the radio wave and allow us to detect the structure of our body. Okay, so that is the magnetic resonance imaging. And believe it or not, it involves 6 Nobel Prizes. I don't know, I don't remember exactly the numbers, but at least 3 Nobel Prizes in physics is about magnetic nuclear resonance. And the other Nobel Prize is about using the magnetic resonance phenomenon to identify different structure. It's a chemistry Nobel Prize. And the last Nobel Prize is on the application of this phenomena in medical science, and that is a medical science Nobel Prize. Okay, that involves 6 Nobel Prizes. So there's a lot of physics, not of chemistry, not of medical science inside this example. So science is like that. We develop basic science, and later people find that the basic science can be applied to enrich our understanding of nature, and also it will change the application of our whole world. So that is the meaning of learning physics and learning science. So that's all for today. I think time is up. We have good time management today. And so we'll stop here. If you have a question for me, then you can ask me now. So I stop the recording.